So how do you build a CNN with Keras? Obviously, you wouldn't want to do this at the low-level TensorFlow layer, even though you could, but CNNs can get pretty complicated. A higher-level API like Keras becomes essential. So first of all, you need to make sure your source data is of the appropriate dimensions and appropriate shape. You're going to be preserving the actual 2D structure of an image if you're dealing with the image data here, so the shape of your data might be the width times the length times the number of color channels. If it's a black and white image, there's only one color channel that indicates some grayscale value between black and white at every point in the image. We can do that with a single value at each point. But if it's a color image, you'd have 3 color channels, one for red, one for green, and one for blue, because you can create any color by combining red, green, and blue together. There are some specialized types of layers in Keras that you can use when you're dealing with convolutional neural networks. For example, there's the conv2D layer type that does the actual convolution on a 2D image. And again, convolution is just breaking up that image into little subfields that overlap each other for individual processing. There's also a conv1D and a conv3D layer available as well. You don't have to use CNNs with images, like we said. It can also be used with text data, for example, and that might be an example of one-dimensional data. The conv3D layer is also available if you're dealing with 3D volumetric data of some sort, so there's a lot of possibilities there. Finally, at some point, you're going to need to feed this data into a flat layer of neurons, right? At some point, it's just going to go into a perceptron, and at this stage, we just need to flatten that 2D layer into a 1D layer so we can just pass it into a layer of hidden neurons. From that point, it just looks like any other multi-layer perceptron. So the magic of CNNs really happens at a lower level. It ultimately gets converted into what looks like the same types of multi-layer perceptrons that we've been using before. The magic happens in actually processing your data, convolving it, and reducing it down to something that's manageable. So typical usage of image processing with a CNN would look like this, at least with the concepts we've introduced so far. There's more we're going to talk about later. You might start with a conv2D layer that does the actual convolution of your data. You might then do a dropout layer on top of that, which just prevents overfitting, like we talked about before. And at that point, you might apply a flatten layer to actually be able to feed that data into a perceptron. That's where a dense layer might come into play. A dense layer in Keras is just a perceptron, really. It's a hidden layer of neurons. And from there, we might do another dropout pass to further prevent overfitting, and finally do a softmax to choose the final classification that comes out of your neural network. As I said, CNNs are very computationally intensive. They are very heavy on your CPU, your GPU, and your memory requirements. Shuffling all that data around and convolving it adds up really, really fast. And beyond that, there's a lot of what we call hyperparameters, a lot of different knobs and dials you can adjust on your CNNs. So in addition to the usual stuff, you can tune the topology of your neural network, or what optimizer you use, or what loss function you use, or what activation function you use. But there's also choices to make about the kernel sizes. That is the area that you actually convolve across. How many layers do you have? How many units do you have? And how much pooling do you do when you're reducing the image down? There's a lot of variance here. There's almost an infinite amount of possibilities for configuring a CNN. But often just obtaining the data to train your CNN is the hardest part. So for example, if you own a Tesla, that's actually taking pictures of the world around you and the road around you and all the street signs and traffic lights and obstacles as you drive. Every night it sends all those images back to some data server somewhere, so Tesla can actually run training on its own neural networks based on that data. So if you slam on the brakes while you're driving a Tesla, at night that information is going to be fed into a big data center somewhere, and Tesla is going to crunch on that and say, hey, is there a pattern here to be learned from what I saw from the cameras from the car? That means you should slam on the brakes. When you just think about the scope of that problem, the sheer magnitude of processing and obtaining and analyzing all of that data, that becomes very challenging in and of itself. Now, fortunately, the problem of tuning the parameters doesn't have to be as hard as I described it to be. There are specialized architectures of convolutional neural networks that do some of that work for you. A lot of research goes into trying to find the optimal topologies and parameters for a CNN for a given type of problem, and you can just think this is like a library you can draw from. So for example, there's the LeNet5 architecture that you can use. That's suitable for handwriting recognition in particular, but it's also a reasonable and very efficient choice for image classification. We'll dive into that in more detail very soon in this course. There's also one called AlexNet, which is also good for image classification. It's a deeper neural network than LeNet. In the example we talked about on the previous slides, we only had a single hidden layer, but you can have as many as you want. It's just a matter of how much computational power you have available. There's also something called Google LeNet. You can probably guess who came up with that one. It's even deeper, but it has better performance because it introduces this concept called inception modules. Inception modules group convolution layers together, and that's a useful optimization for how it all works. Finally, the most sophisticated one today is called ResNet, that stands for Residual Network, and it's an even deeper neural network, but it maintains performance by what's called skip connections. It has special connections between the layers of the perceptron to further accelerate things, so it builds upon the fundamental architecture of a neural network to optimize its performance. And as you'll see, CNNs can be very demanding on performance. So with that, let's give it a shot. Let's actually use a CNN and see if we can classify real-world images using it.